Assalamualaikum and a very good day. We're from Group 5 and we will do a presentation on the analysis performed on electromyography signals. So this here is the representatives of the project. We have Hibat, Raghd, Melinda, and also myself, Ayu, and we will together discuss on how we will analyze the EMG signals. So based on this slide, EMG, what is EMG? So EMG or electromyography is actually a device to measure the electrical activity of muscles during contractions that will help us understand muscle activation or motor control in our nervous system this way. This is crucial in biomedical engineering for clinical diagnosis, rehabilitation, monitoring, and even optimizing sport performances as a new innovation in biomedical devices. However, analyzing EMG signals will come in a few challenges, such as non-stationary signals, where frequency and intensity will change over time, and it'll be susceptible to noise and artifact, which is something that we need to overcome it to gain a better wavelength throughout the system here, which we need in order to accurate our interpretation here. For this part, we need to analyze the electromyography signals itself. So in order to do that, we need to perform a time frequency analysis. This one here we have two ways, which is the short time Fourier transform as well as this wavelength transform. So the definition of time frequency analysis by itself is actually to understand how a signal's frequency changes over time, which is important for signals like EMG. Short-time Fourier transform is a process where we split the signals into equal time windows in order to analyze that will give a steady resolution for both time and frequency. However, it struggles with the fact that it cannot overcome a very fast or dynamic changes. So that's where wavelength transform comes in handy, where it is more flexible. It uses the windows in order to adjust in size, offering a better detail for higher frequencies and broader changes for low frequencies. This will make it great for analyzing for sudden or highly dynamic signals like EMG.
And now we move on to the data set that we collected. The data we obtained from a research paper, a data set of a simulated bicep muscle electromyogram signal by using Rossler-Chaotic equation, which focuses on EMG signal analysis specifically for studying muscle activity. The purpose of collecting these signals is to analyze the electrical activity generated by the muscle contractions, which is relevant in fields such as biofeedback, prosthetics, and muscle fatigue monitoring. The file we used contains data from one of the 10 participants, a right-handed female, who participated in the study. The sampling rate of the data was 4,000 Hz, meaning that 4,000 samples were taken per second, and the duration of each recording was 414 seconds, providing a time frame of over 6 minutes, during which the muscle activity was continuously recorded. This allows for a detailed analysis of the EMG signal frequency and temporal characteristics. Okay, so now before we move on to the EMG signal analysis, we wanted to ensure that our data set is accurate and actually makes sense, so we decided to run a quick code in MATLAB to plot the data. So the first part of the code here is just to load the data into MATLAB and to check if the file can be opened and the content can be read through MATLAB. The next part was to read the entire file at once, which means that MATLAB would scan and load all the values in the file into the software, and then we can close the file. Next step was to check if the file contains any data, which is actually the most important part. We wanted to ensure that the data is all numerical throughout, and all the data is can be interpreted through MATLAB. So we checked if the file contained the data, and then we used time extraction to identify the time column and this corresponding signal column. So we had the time intervals beside the column that defines the time intervals and the corresponding EMG signals to it. The last part was just a plot. We plotted the time against the EMG signal. We just labeled the X and Y axis and utilized an if loop to show that the file does not exist if the file does not have any data. Now, on the other side, as you can see, we have the result of the plot of the EMG signal. We compared it to photos of how an EMG signal would look like of a contracting muscle, and we concluded that the data in our file is actually relevant. Let's move on to the short-time Fourier transform analysis of our EMG signal. The first step, just like the other code, is to reload the data into MATLAB and to check if the file can be opened and can be read. The next step is to read all the file at once, which is uploading all the data in the file into the software. Next step is to check if the file contains any data, which means that we need to scan through the software needs to scan through the data to ensure that all the data can be interpreted. Okay, and then we need to extract the time and signal columns, which is just like we mentioned before, is to define the time intervals column and the corresponding EMG signal to it. And then now here's the part that's different. We set the parameters for the short-time Fourier transform. A window size of 256 was utilized. An overlap between the segments in the sample was 200. The number of FFT points was 512, and the sampling frequency is derived from the time data. Now we computed the short-time Fourier transform using the spectrogram function. SFT is equal to spectrogram, EMG signal, window size, overlap, and FFT, and sampling frequency. The last part was just to plot the magnitude. We used a logarithmic scale for better visualization. And then we set the x-axis against the y-axis, used the color bar. Now, as you can see on the other side, this is the spectrogram that represents the short-time Fourier transform of the EMG signal over time. The x-axis shows the time and the y-axis shows the frequency. And the color scale represents the signal amplitude in dB. It highlights the frequency content of the EMG signal, and it's showing a dominant activity at lower frequencies and variations over time.
Okay, so let's talk in details about the coding. So for the main feature, we have 5 steps in total. So the first step is going to be about the file handling. We handle the file by make sure the file first exists, download it in MATLAB, and then if it existed already, we open and we read the content, and then we make sure that there's 2 columns mentioned. As first we have the time data column, and then the second column we have the AMG signal data. And then if the file is missing, obviously it's going to be error in the code. This is for the first step. As for the second step, it's going to be about the signal characteristics. So the code will extract the total duration of the signal, the difference between the first and the last point, the last point of the time for the duration. And then lastly, we're going to be calculating the sampling rate by obviously listing down the formula fs equal 1 over time 2 minus time 1. Then step number 3, we have the downsampling. This is just to make sure that if there's a large data or something, the downsampling would manage it. And then for step 4, we have the wavelet transform. So for the wavelet transform, we make sure that we have the right wavelets. There's few kinds of wavelet, but the one that we've been using in EMG signal is going to be the Amor, or it's called the Morlet wavelet. And then we adjust the time frequency representation by using the sampling rate. This is for the wavelet transform. And then lastly, we have step 5, which is the visualization. So basically, it's about the raw EMG signal plot and also the transforms colorgram plot. This fifth step is going to make sure that we plotted the signal by the putting the x-axis as the time, the y-axis that as the amplitude, and same for the wavelet, the x-axis, the y-axis, the color map, the purpose of the code to finally give us the raw EMG signal plot and also the wavelet transform waveform. So this is it for the MATLAB code. So after finishing everything, we run the code, and this is the final signal. As you can see, the wavelet transform for EMG signal. We obviously this signal it matches the raw signal we got also, so that's how we know that the final simulation result is correct.
So I will continue with the part discussions. For this part, I will explain about few features that can be controlled for the SDFT and wavelet transform analysis. Started with the time frequency resolution, SDFT has a fixed depends on the window size. Meanwhile, for wavelet transform is adaptive and varies with the frequency. And the next one is suitability. SDFT have stationary or periodic signals. Meanwhile, the wavelet transform is transient and also non-stationary signals. Frequency localization for the SDFT is clear, meanwhile for wavelet transform is more accurate for varying frequencies. The next one is time localization for the SDFT is poor for rapid changes. Meanwhile for the wavelet transform is good for capturing signals. The next one is computational complexity for the SDFT is lower, depends on the window size and length of the signals. The next one is wavelet transform is higher, depends on the wavelet type and scaling. The second last one is interpretability. For SDFT is straightforward spectrogram, meanwhile the wavelet transform is require understanding of wavelet types. The last one is applications. SDFT require periodic analysis, meanwhile the wavelet transform is event detection. So for the next one, I will explain about strengths and limitations. For the strengths of the SDFT, it includes easier to implement and interpret. And the second one is suitable for overall spectral analysis where time resolution is not critical. The next one is strengths for wavelet transform. It includes captures the both times and frequency variations. The next one is excellence for analyzing non-stationary signals like EMG. The limitation for SDFT includes non-ideal for retention EMG signals with varying frequency content, and the next one is fixed resolutions, restrict detailed analysis of rapid changes. Meanwhile, the limitation for the wavelet transform analysis is require careful selection of the wavelet types and scales, and the next one is computationally expensive, especially for long duration signals.
To summarize, our analysis emphasizes the importance of short time Fourier transform and wavelet transform in processing the imaging signals. While SDFT provides consistent resolution for moderate signals variation, wavelet transform will adapt well to a higher dynamic changes. This methods both plays a role in biomedical engineering in order to support diagnosis, rehabilitation, and as well as therapy. That said, everything has a pros and cons, where SDFT has limitation with rapid signal changes, and wavelet transform will require significant computational power. So, moving forward, refining these techniques will be key into achieving a greater accuracy and efficiency in practical applications.